Okay, so tonight I want to talk about an infographic that Radix put out on their website. It's fascinating because it goes into great detail through a series of different chapters, if you will, on how it works, why they feel it's better, and it's very interesting. I mean, the goal is scalability without sacrificing decomposability, security. You don't want things too centralized. You don't want uh, lack of security. And you want to process things as quickly as possible. And as you know, if you've dealt with Ethereum or Bitcoin, sometimes those transactions can take a while, particularly Ethereum. You buy something, some Ethereum, and you're looking, or you move it between wallets, and you're looking, saying, where did my Ethereum go? I'm getting nervous here. Did I, send it to the wrong place or something like this? That's because it's slow. Um, and they do talk about in later on, and I think they have a little summary of it in the end of this. Yeah, about the trade-offs. So the problem is there are three solutions or two solutions that we've seen, pushing more transactions down the same chain. That can still get crowded. Sharding. The problem with sharding is that it sacrifices, scalability, decentralization, and security. And you really need all of them. So you don't have the interoperability, you have silos. Um, so that's kind of the problem. Scalability while preserving atomic composability, decentralization while maintaining security. And they have this little chart here. Current central control of nodes, increase in scalability, sacrifice of decentralization. Sharding increases in scalability, but sacrifices atomic composability. In other words, you can't break things up. Now, their argument, and this first page here goes through a lot of their stuff, and then you can delve more in depth. Basically, they break their network. It's not, they don't even call it a blockchain. It's this network, or they call it shard space. And each shard, which is almost infinite, is served by a bunch of validator nodes. And they're talking about here you have the Radix engine for applications, and Cerberus for consensus. And this would represent our components or programs. And remember, we saw looking at the samples that a component is essentially an instance of a package, which is basically a definition of an object, a component. And so they have all of these, and then another very important concept that they discuss here is substate. They're similar to the unspent transaction outputs in Bitcoin, but they don't have to be, extra Bitcoin left over after a transaction. They can be data, they can be code, they can be anything. So you have a shutdown and a bring up, and that's how you have your state transition. And each substate has a unique ID. But here's a good example where they talk about a transaction, a very simple transaction. So shard 1 shuts down Alice's token A substate. Shard 2 brings up Bob's token A substate. So shard 3 shuts down Bob's token B substate. And shard 4 brings up Carol's token B substate. And shard 5 shuts down Carol's token C substate. And shard C brings up Alice's token C substate, and they all agree, and here's your transaction. So what this looks like is Alice gives a bunch of A to B, B gives a bunch to Bob, Bob gives a bunch of B to Carol, and Carol gives a bunch of C back to Alice, and that's their transaction. So here's a little diagram. So this is what's really nice about it, is they go through and they have little diagrams and go into emergent consensus, how nodes come to. So basically, these shards trade information and come to an emergent. They call it they kind of braid, so they say yes, 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 yes. So they merge the proposed vertex, and then they do more merge. So they're basically cross-checking each other, and eventually they agree. And I think the reason they call it three changes, use kind of a three-step process here. So they go into great detail, and partial ordering is another interesting concept. It's basically saying if two transactions are not related, why should we care what order they're transacted in? We don't. They doesn't change anything regardless of what order you transact them in. So that's another very important concept. And the nodes, of course, keep the records of the transaction and the proof. And they're chained to previous, each vertex is chained to previous vertex via hashes, and that's how they obtain total consensus. And this is stuff that again, they break this down here, and we'll probably want to go through some of these, because way at the bottom they lead you to the rest of the discussion. So anyway, I'm going to put a link to this infographic here. I think it's a very nice way of explaining how everything works, as opposed to your typical white papers that takes quite some effort to get through and can be a bit of a pain. So hopefully this has been interesting, and I encourage you to check out this this series here, and of course ask questions if you have, and I will try to answer them. And I will speak to you next time. Take care.